Hello everyone, November 23rd. Alright, I'm catching a deadline on the paper, so spend a whole day writing. Man, that's never a fun thing. Anyway, I have to do world word search. What's that? MN grid and a string word. Return true if word exists in a grid. The word can be constructed from letters of sequentially adjacent cells, where adjacent are horizontally or vertically neighboring. The same letter may not be used more than once. Okay, so DFS? Yeah, DFS with backtracking. Just search. Because you look at this, it's a 6x6. Okay, it's a teeny tiny thing. So you just start from one. I mean, you don't have to start from every one. You start from the one that matches, and then you just go, right? And just go around, and we do have to record which one you have been to. Okay, yeah, it's not a big deal. 24. Yeah, my paper is due on the 24th. I need my revisor's help on that. He's helping, so that's all right. Deadline now. I've been dealing with deadlines all through my life. It's okay. Yeah. All right. So what do? We are going to say search. Okay, say def search. Okay. And we're gonna have a we can change on the board. So all we need to do is ing, right? And we have mn always set us up. Okay, and then with this one, I'm gonna return a boolean value, and then we just say, oh, we also need index. That's on the word, right? So we're gonna search. We're gonna say if word, if board ij is not equal to word index, and return false. Otherwise, if it's equal to, then we say board ij equals this. So this is visited. Then for didj in what? Oh my god. Yeah, we've done this many times. Okay, and ing equals di, j equals dj. If 0 ni and 0 j and board ning is not equal to dot, it hasn't been visited, then we say search ning index plus 1. If it's true, we'll return true. Otherwise, try to search the next one. Blah, blah, blah. Then we will say board ij equal to, oh shoot. Oh, actually we know, because it's equal to word index. So we just give it back, word index, and now return false, right? So we're gonna say for I in range m, j in range n, if board ij is equal to, I see. No, I don't like it. It's equal to word 0. Then we'll search. No, we can just search directly. Yeah, I want to call search directly. And just call search ij 0. If it's true, we'll return true. Alright, otherwise we'll return false. I shall do it. I'm a little bit sick. Sick from my throat. Board would exist. That ain't right. String index out of range. Oh, that's true. Hold on. Come.
Before you would come out.
Oh, you can just go hold him.
He's about to go into bed. He's under the bed.
It's okay. Alright, we forgot one thing. Index has to be if index is equal to len word. Wait. Oh, yeah. I have no true. We say if index is equal to len word, that means we have already succeeded. There we go. Yeah, we forgot the and case. Oh, that was a lot of attempts. What? It's probably the same mistake here. What? Come on. That does not make any sense. Yeah, this is true. Ooh, we don't go to the next one. Holy shoot. Oh, that is the problem. So we have to check. when you say if this is the last one and board ij is equal to what index, the last one equal to the next, then we will just say true. Huh. Interesting. Interesting. It no longer works. Huh. Oh, I see. Yeah, everyone, go out. Are you telling me to pre-check the whole thing? Hold on. So do we check? Okay, it doesn't cost too much to check. Yeah, we can check. Actually, we can do like a counter check. Right, it has to have at least the same number. If we have, let's say, 2 B's in Word, but only 1 B in board. All right. Pre-check. BC equals counter. How do we do this? We can say for row and board counter row, and then we think we can sum this. I'm not sure. Nah, I don't think we can. Int and count. We can chain. Madre mia. Let's do chain. So we can say we're going to chain board and then counter dude. That shall be false. All right. God, it take a while. A36, yeah, that's, so the BC. WC equals counter word, right? Pre-check for letter and count in WC dot items if BC letter is smaller than C, then we'll return false immediately. Yeah, as a pre-check. Okay, so we have a pre-check. That must be a new test case. Come on. Admit it, that's a new test case. Here we go. Oh, man, I'm curious. $84. $57. I do pre-check as well. And now it's required to do pre-check. I use this, so I don't have to do it. It's the same thing. I do this one directly. Yep, the pre-check is important. The pre-check is crucial now because the test case has increased and has included the case where if pre-check is not included, it will TLE. This is the, I don't know how many times, 4th? 1, that's considered the same. 2, 3, yeah, this is the 4th, this is the 4th time. What's the runtime on this? I mean, it's every has to go, this has to go, this has to go. So I think it's ON tripled, right? On average. Because this, we want to do a search. This is ON squared. So you have to visit every single one at least once. And then we do this. Oh man, that's not, that's OMN. MN. That's MN. This is also MN. Oh, okay. So we've done this. Okay. Another difficult one. Maximum number of nice divisors. People don't like this one, huh? You're given a positive integer prime factors. You are asked to construct a positive integer n that satisfies the following conditions. Number of prime factors of n, not necessarily distinct. What the hell does that mean? It can be not distinct, is at most prime factors. A number of nice. the number of prime, which just means it doesn't matter. It doesn't matter. Like if we have a large, like the prime factor is large, it doesn't matter because we can repeat. But if it's small, right? If it's small, then at the most, I see it's setting a ceiling, right? So the number of unique prime factors should be smaller or equal to prime factors, because if the number of unique prime factors are smaller than prime factor, then we don't work. So we have is that the limit, right? The lower bound of the number of unique prime factors. And the number of nice divisors of n is maximized. A divisor of n is nice if it is divisible by every prime factor of n. For example, n equals 12. Its prime factors are 2 to 3, then 6 and 12 are nice divisors, while 3 and 4 are not. A divisor of n is nice if it is divisible by every prime factors of n. Number of nice divisors modulo this. I see. We can get the prime factor. We can. Especially if we get a list of prime factors. We just go divide them. 10 to the 9th. Oof, that's a lot of prime factors out there. Yeah, 10 to the 9th is a lot. You're given a positive integer prime factors. You're asked to construct a positive. I'm going to construct a positive integer n that a number of prime factors of n is at most. So I can construct it, okay? And then I want to maximize the nice divisors. A divisor nice is divisible by every prime factor of n. I see the example. I only give us one example. Find prime factors and it has 6 nice divisors. Divisor has to be a divisor of 200 and have, because I only have 2 and 5. So I just go 10. And then I can do 2 times 10, 4 times 10, 6 times 10. And 2 to 2 can go 5. So yeah, so 2, 5. Now we have, so 2, 5 has to be included. Right, 2, 5 has to be included. Now we have 2, 2, 5 left. And then the question is, how many can we get from 2 to 5? Well, we can get, lordy, I mean, how many we can get within each? That's just 1, 2, right? So I have 2 and 4. this will have 5. And then that's 3. And then we can do then we can do, so we have 2, 4, and 5. Right, and then because they're all different, so this and this, so we have 10 and 20. So now we have 2, 4, 5, 10, 20. That's 1, 2, 3, 4, 5. What's 6 is 1? Oh, 10 by itself. So that's 5 plus 1, 6. Well, in that case, we want the prime factor as large as possible. We want it to be n, right? Because if it's small, then we are reducing the number of nice divisors. So but we can also do, I don't know, 5. We can say like 2, 2, 2, 3, 3. Right? 2, 2, 3, 3 is the same. So we want 2 times 3. Right? And the remainder is 2, 2, 3. It's the same thing. We got 6. Because 2, 2 can produce 2. 3 can produce 1. When them combined together, we can produce 2. And then we can produce 5 plus 1 is 6. That's the same thing. Can we put all of them as the same? Let's say 2, 2, 2, 2, 2, the same. Well, if we do them the same, then it doesn't really matter, right? A nice divisor, anyone is a nice divisor. Then the question is, how many can we produce? Well, if we have this, then basically that's just 1, 2, 3, 4, 5. We can produce 5. 2, 2, 2, right? 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2. That's 5. And it's smaller than mixed in. Okay, how about I'm mixing 1? Let's say 2, 2, 2, 2, 3. Again, 2, 3 will be taken. And then we have 2, 2, 2 left. Now 2, 2, 2 can produce 3. So in total can produce 4. Because that's 3 of this plus 2, 3 itself. Right? So 2, 2, 3, 3 is good. And 2, 2, 3, 3, 3, that's the same. But what if we mix in more? If we mix in more, which we say, let's say 2, 2, 2, 3, 5, then we have to use 2, 3, 5. Right, we're sacrificing. Right, we're sacrificing. Because we need more to produce this nice, like 1 more to produce a nice. And then that one cannot contribute to producing the other possibility. So I think it's pretty fair to say that it has to have only 2 prime factors. So for 8, it's going to be, but how many, right? How many? Well, the more we have, the more we can multiply. So for 8, I would say 4 2s and 4 3s. We pick 2, 3 out, and then on the left hand side we can produce 3. Right hand side we can produce 3. Right? So it'll be 3 plus 3 plus 3 times 3 plus 1, which is 6 plus 9 plus 1, which is 16. But the answer is 18. Holy crap. Alright, so let's say 5 2s and 3 3s. Right? So now we have 4 and 2. So we 4 plus 2, right, plus 4 times 2 plus 1. So 6 plus 8 times 1. That's 15. That's actually smaller. Dude, how's 8 work? 18. How does 18 work? Oh, we might have to mixing another one. Okay, let's say we're mixing another one. So we have 3, right? Then we'll take 3 out. We have 5 left, right? We have 5 left. Then we can say 2, 3, 5. 2 left. So 2, 2, 3, 3. So this one we have 2. This one we have 2. This one we have 1. So it's 2 plus 2 plus 1 plus 2 times 2. That's only 10. Apparently not. Huh. How would you get to 18? Alright, we probably have to problem like this. We need more examples, right? This is not really helping. Yeah, let's get all the help that we have. Right? We need to find a pattern. Like so far there's no pattern. I don't see the pattern. 1 is 1. Okay? So this is the result. You can just put it here. Okay. One is the 1. 2. 2, 3 is actually going to produce 1. So 2, 2 is the best. So we have 2. 3, we can go 2, 2, 3. That's going to be 1. That's going to be only 2. So 2, 2, 2 is the best for 3. 4. All the same is going to be 4. Mixing 1 is going to be 2. It's going to be 3. Mixing 2 is going to be 1 plus 1 plus 1 times 1 plus 1. That's 1, 2, 3, 4. That's also 4. So 4 is 4. 5 is 6. We already done 5 is 6. So 5 will be 5. We're mixing 1. That'll be 3. That'll be 4. We're mixing 2. That will be 2 plus 1. Right? Plus 2 times 1 plus 1, 6. Okay? So 1, 2, 3, 5 makes sense. 6. 6 is 9. Okay? So 6 is 9. Let's see. Again, 6 by itself is 6. If I take 1, is going to be 5 plus 1. That's 6. Right? Like 5 or something like this. And I do this. Oh, actually, no. No, I have to take 1. So it's way 2, 2, 2, 2, 2, 1, 2, 3, 4, 5, 3, right? 2, 3, that's actually 4. Actually 4 plus 1 is actually 5. So now we go, so 2, right? So we take it away. Then it's going to be 3 plus 1 plus 3 times 1 plus 1. That's 7. No, that's 8. Right, 3 plus 1 plus 3 times 1 Are you not considering something? Oh, I am not considering everything. Hold up. So we have a 3-1 situation, right? So minus 2. Whatever this is, we minus 2. So we got a 3-1. And we can do 3 plus 1 plus everything here. Pick 1. Everything here, pick 1. That's 3 plus 1. But we can go here because this is 2, 2, 2, 2, 2, 2. And the other side is 3. So I do this, this, and this. Nah, that's already considered everything. And then plus 1. Yeah, that is 9. That is 8. 2, 2, 2, 3, 3, 3. So that's going to be 2 and 2. Right? So we have 2 and 4. 3 and 9. So we're looking at 2 plus 2 plus 2 times 2 plus 1. Ew, that is 9. Okay, so 9 is done. 7. That's the one. 7. Okay, 7. Again, if it's 7, that's going to be 7. If you take 1, then it's be 7 minus 2, it would be 5. Right? It would be 5. Then we have 1, 4, 2, 3. Right? If it's 1, 4, it's going to be 1 plus 4 plus 1 times 4 plus 1. Right? What's that? That's 5. 5 plus 4, 9 plus 1 is 10. 2, 3 is going to be 2 plus 3. 2 times 3 plus 1. That's 5. 6. That's 12. That's also right. But how come 8 is not right? We do 8. 8 minus 2 is 6. So we have 1, 5, 2, 4, and 3, 3. So that's 1 plus 5 plus 1 times 5 plus 1. Oh, that's 12. Dude, you didn't consider that? 2 plus 4 plus 2 times 4 plus 1. No, that's 15. No, I'm right. That's 12. We're looking for 18. That's 3 plus 3. Right? Time plus 3 times 3 plus 1. Yeah, that's 16. So there's something we're not considering, which is, I just realized, because on the left hand side we can pick 1, or we can pick 2 at a time, or we can pick all of them, right? So it's going to be, it's not just 3. If I have 3 values, right? If we have 3 values, nah, I don't think so. No, that's that's not right. How'd you get to 18? Huh. Yeah, let's consider all of them. Yeah, if we cannot figure out this 8, it's not gonna work for you, man. So this one has to take, right? They should give us a example. I mean, yeah, we have to go 3 prime factors, right? But if we go 3 prime factors, ooh, hold on, 3 prime factors. Hold on, let me see. 2, 3, 5, right? So the remainder, when we have 3, now we have 3. What do we do? Well, like I said, best case scenario, we include all of them. 2, 2, right? 3, 3, and 5. So now it's just how many different combination? 2, 2, 3, 3, 5. So because it would be 2, 4, 3, 9, and 5. Holy crap. Did you just realize what you just did? Any of them and any combination of them. No, not any combination of them. This is a group. This is also a group. This is a group. So any combination of this group will work. Hoo-wee. So by themselves, right? So it'll be 1, 2, 3, 4, 5. So I have 5 by themselves. Plus the original 1, right? Then plus, well, we can do these 2. That's 2 times 2. That's 4. I can do these 2. That's 2 times 1. That's a 2. I can do these 2. That's a 2, right? And I can do all of them together, which is 2 times 2 is also a 4. So we have 5 plus 1, that's 6. 6 plus 4 is 10. 10 plus 2 is 12. 12 plus 2 is 14. 18. Got it. That's 18. And we have seen the secret. Oh man, how are we gonna compute this? How do we know it's gonna be more prime factors? Holy crap. What happened if we add a new prime factor? Right, whatever we have previously, let's say that's the maximum. Now I need to add a new one. So when you add a new one, you can make a choice. You can add the one that exists before. All right, if you add one that exists before, then depending on the previous split, right? If we have two variables, if we have two, then if we have three, then we better have three, because otherwise it's taken away from having two, right? So we can find the maximum of having two, which most likely is landed in the middle, like evenly split. That's when we have the maximum. There's no proof. There is a proof, like the multiplication, if the two values are similar. If the sum is the same, then when the two are similar, the closer they are, the larger the value is. So for 2, it's definitely we should evenly split them, so I can get the maximum for 2. How about for 3? Well, we can say for 3, they shall also evenly distribute. So we can go a little bit like greedy, say they have to be evenly distribute, right? Because for 3, I have 3 groups. What's gonna happen is each group have the totals, right? So yeah, each group has their totals, and then you can pick 2 of them. We're gonna compute theirs, and then we're gonna compute the 3s. Damn, how are you gonna compute that? It'll be a list of values, okay, and then what you doing? Let's say we have A, B, C. Right, what we want to compute is A plus B plus C. Right, and then AB, BC, AC, and ABC. That's what we want to compute. Now A plus B plus C. And if we have 4, yeah, it's getting more and more complicated. how do we get it into shape? Like, I know I can assume, right? Because it's gonna follow the same recipe. So if multiplication, if the closer the numbers are, and the bigger we can get if the sum is the same. Now the sum is the same, right? We can have everything, the sum is the same. Hold on. What is that's a squared, b squared, c squared, ab, ac, bc, right? But if we have a, b, c, d, we can produce abc, right? abd. Dude. Of course, I'm plus 1 as well. Huh? What? That doesn't make any sense. Hold on. Let's calm down and then redo the math. Alright, so we say we have a plus b plus c plus 1 plus ab plus bc plus ac plus abc. And then we say a equals 2, b equals 2, c equals 1. That's 2 plus 2 plus 1 plus 1 plus 4 plus, no, plus actually 4 plus 2 plus 2 plus 4. That's 18, okay? If we only have 2, that's going to be a plus b plus 1 plus ab, right? That's everybody else. Like a equals 2, or for as 5, so a equals 2, b equals 1. That's a equals 2, b equals 1. So that's 2 plus 1 plus 1 plus 2. That's 6, right? What's this? This doesn't mean anything. That's just a plus b plus 1. And if we only have 1, then that's just a by itself. So every time we increase, if we have 4, it's going to be a plus b plus c plus d, right? Now we have ab, ac, ad, bc, bd, cd, abc, abd, and acd, and then bcd, and then abcd. That's bonkers, man. That's not gonna work. Gotta be a way. 2, then that'll be 3. Right, the closest 2 and 1. So that 2 plus 1 plus 1 will be 6. And if I pick 3, it'll be 1, 1, 1. So I can use this, but it's a difficult one to compute. Nah, if you go 3, you have the minus 3, so I should have 2, only have 2 left. That's not possible. That's not possible. Huh. Okay. Yeah. That's not possible. So are you saying if we can't afford it, we should always afford it? And how about 6? 6. So 2, 2 is 10. Is 9, right? We can do 3. So we have 3 left. So it'll be 1, 1, 1. So that'll be 1, 1, 1, 1, 2, 3, 4, 5, 6, 7, 8. That's only 8. So we can say from 5, right, 5 is going to be 2, 2, 2, 3, 3. And 6, right? 6, we can add a 2. And we say add a 2. Yeah, we can say I want to add a 2. No, it's not going to work. If I can compute and I get an easier way to compute, that would be big. But I don't have a way now. I don't have a way to compute it fast. Like all combinations, the sum of all the combinations. I know how many there are. Right? That's 2 to the 3 minus 1. That's 2 to the 4 minus 1. I know. Can you produce all of them? But even if you can, how can you guarantee that is the largest? Unless we can compute this in 01 time. I want to find the largest. Yeah, that's the question. Given the remainder, what's the biggest sum that you can achieve? Yeah, that's it. No further. Oh, you gotta be kidding me. I factored it. Wait. No, that's 4. That's AB, A plus AB, A plus B plus 1. Yeah, isn't that just A plus 1 and B plus 1? Yes. Dude, come on. You can do this. Factor that. Factor that. Come on. Get your math back together. We can factor it. Let's see. We like AB plus A plus BC. ABC, right? So we have A plus B, 1 plus C, plus 1 plus C, plus AB, 1 plus C. Yeah, we get A 1 plus C, and then we have A plus B plus 1, plus AB, A plus B plus 1 plus A. Is this C plus 1? Oh shoot, A plus 1, B plus 1, and C plus 1. Man, you gotta be kidding me. This is A plus 1, B plus 1, C plus 1, D plus 1. I think we found it. I think we found it. That's just 2. That's A plus 1 times B plus 1. That's 3 is A plus 1 times B plus 1 and C plus 1. That's 3 is just keep going. So, I mean, this is not. But we say we want them to be evenly distributed, right? Do we have a theorem that, because these things added together is the same, right? So when we have the same sum, and if we want to find the maximum product of these guys, then they have to be evenly distributed. I mean, we can, let's say we have x plus y equals a constant, right? Then xy should equal to x times c minus x, which is minus x squared plus xc. So this will achieve the maximum if its derivative is 0. So it's minus 2x plus c equals 0. So when x equals to c minus 2, right? So if we do, let's say x plus y plus z equals c. Now I want to assign x, y, z, the maximum of x, y, z. So we can say minus z. No, well, no, we say z will equal to x plus y minus c. So that's xy times x plus y minus c, the maximum of this, right? Okay. Maybe we do partial derivative for this. Do we have a theorem for this? How do we search this? Max product of a series with constant sum. Yeah, something like that. AMGM. Assume this, maximize the product. Then this, assume there are indices ij with xi larger than xj plus 1. Then xj plus 1 times xi minus 1. Okay, xi is larger than xj plus 1, so they're different by more than 2. Then we say this, not this, because this is larger than xj times xi, because this xi is larger than this, and hence by replacing xi to xi minus 1. So if the 2 is bigger, or is different by more than 2, then if we get the bigger one, because xi is a bigger one, get it smaller, which it's still larger than xj, right? But it's just, it gets closer. So xi minus xj is larger than 1. And what we find out is xi, xj, xi minus 1 times xj plus 1. So what's the relation between this? If we go minus 1, so xi minus 1 is larger than xj, but xi minus 1, it might be equal to, right? Because there's no guarantee xi minus 1 is larger than xj, okay? But 1 xj plus 1, so xi minus 1, it might equal to xj minus 1. Or, because they're all positive integers, so xi minus 1 is larger than xj, so it can be larger by 1, right? Then if I added, they were equal. If it's by 2, then what would it be larger than by 3? It could be, but that's not the point. The point is, if we construct these two, then they're is larger than these two together. So if we do this, we obtain a solution. Yes. We conclude this smaller or equal to 1 for all I. Wait, hold on. So what we prove is if we swap xi to xi minus 1 and xj to xj plus 1, we'll get a better deal. Right? So initially xi is larger than xj plus 1. So xi is here. Then we say we reduce xi, right? Then if xi is still larger than xj plus 1, then we can further reduce. So we further reduce xi, we further increase xj, right? And then as long as there is still room to do this, we can always make it better until a moment when they're equal, right? Or it's equal to 1. So we'll get to this point for everyone. That is the proof. That is the proof. At most, 2 distinct values occur among all the xi. K times A occurs at least once. Then we have S equals nk plus k. Yeah. And 0 smaller k smaller than n. K equals S mod n. Oh, wait, hold on. S equals NA plus K, right? If S equals NA plus K, and then K is 0 to N, so K is the remainder. Holy crap. So N, we don't know what N is, but it's gonna be, no, we know N. N is the total number of values. We don't know A. So we say it'd be N times something plus a K, which is between 0 and N. So we can say K is, yeah, S mod N, and A is S divided by N. We take the floor. And the corresponding is A to the this plus. Holy crap. This is, oh wow. Ooh. Damn, that's so good. Wow. So for this problem is the same, right? So what we're gonna do, we're gonna try all of them, right? So given a value, so what we're gonna do is say we want a 1. If we want a 1, that's just by itself, right? That's N. If we want 2, then the N is gonna be, well, okay, the prime factors, right? PF. That's gonna be PF. If we want 2 factors, so it would be PF minus 2, right? And then the remaining number is gonna be PF minus, wait, what? So I take 2 out, right? Then we have the remaining values. And the remaining values has to be larger or equal to 2. Larger or equal to 2. Otherwise, it's not as good as doing the other one. So we can do this, and then we do this. See if it's larger or equal to 2. If it is, then we can compute, right? If it is, then we can compute. How do we compute? So we grab the value, right? We grab PF minus however many, we can say K. We want to divide it into K. Yeah, it has to be larger or equal to K. Then we took PF minus K. That will be the N, right? That will be the total N. So that's N. Then what we want to find is we have all these values, right? Add up to N. We want to find not theirs. We don't want to find their value first. So their value is going to be, no, that's not, that's S. That's a total add up to S, right? That's the total add up to S. Wait, hold on. What the heck is S? No, that's the total number, right? Wait, hold on. Hold your horses. What do we have here? What we have, right, is the numbers. Yes, the numbers, the total numbers of each one, of each prime factors, right? And then the total numbers add up to S, which is PF minus K. And then, what else do we have? We have K. K is N. So we can't, not K, we can do N, right? So PF minus, we have S, so we have N. Then we can find the smaller value. It doesn't matter smaller value, so we can find the one value. One of the value, we can call it A, because there's only going to be 2 values. A is going to be S divided by N. B is going to be S divided by N plus 1. Okay, now the power. Right, now the power. The power is going to be N minus S mod N for the smaller value, and then we have for the bigger value. Now what happens is they're just going to be plus 1, right? So what we're going to do is just going to be A plus 1 to the N minus S mod N times B plus 1 S mod N. Okay, let's try. We can start with, let's just do 8. Okay, so for 8, what do we have for 8? So for 8, PF is equal to 8, right? Let's say N equal to 2, then S equal to 6, and 6 is larger than 2, so that's good. So then A equals 6 divided by 2 is 3. B is equal to 4. Right? So the total is going to be, and S mod N is 0. So we're gonna have is 3 plus 1 to the 2 times 4 plus 1 to the 0. It's 16. Okay, So if we take n equals 3, and then s equals 5, then a is equal to 5 divided by 3 is 1, b is equal to 2, then we do 1 plus 1, right? 1 plus 1 to the n, and then 3 minus 5 mod 3, that's 2, times 2 plus 1 to the s is 5 mod n is 2. So that's 2 to the 1 times 3 to the 2. 18. Holy crap. Dude, it works. Oh. I'm in the wrong place. Okay, so yeah, I'm all out today, man. I'm all out. So we have the prime factors, right? So what we're gonna do is rest equals 0. Now rest can equal to prime factors, right? Then for n in range n equal to 1. While true, now n equal to 2. S equals to prime factors minus n. If s is smaller than n, then I'm gonna break. So what we can just do is while this is larger or equal to n, s equal to this minus n, right? And then we have the s, and we have a, b equals s divided by n. S, I can just say a equals s divided by n. B equals a plus 1. All right, and we can say k equals s mod n, and rest are equal to maximum rest. We cannot even mod here because it won't know. So that's gonna be a plus 1 n minus k times b plus 1 k. Now we return res mod mod. Three, 4, 6, 6, 9, 7, 12, 8, 18, 927 10 36. Oops, something is not right. I forgot. N plus equal 1. There we go. Let's get a test cases. Oh, shoot. Yeah? But I'm not inside. I have the Python versions. I redid PyInf, so that's actually not really helpful. Yeah. But why am I not in the Python environment? I'm under the Ruby environment. Oh, something is not right. Something is not right. It's okay. Oh, I can't even do that. Whoa. I completely break it. Shoot. Man, yesterday I was doing all those things. Didn't realize. Get text. See if we can just uninstall it. Okay, uninstall get text. No. How about brew link? Let's see, maybe we do this. Unlink and then relink. Nope. Still no good. Yeah, this seems to be homebrew. Yeah. No such file, no such file, no such file. The heck? Okay. I guess. I don't know. Alright, so I just want to get Python to work. So it's not in here. It's not in here. Maybe I just need to add to the path. Homebrew bin. I have homebrew. open. But it's not looking into those places. That's not helpful. Oh, come on. I'm looking at this, right? You can make it and you can link it. It's all because yesterday. That's so stupid. All these paths. I tried, but it didn't really work. No, I don't want to do this again. I did it yesterday. Nope. That is not the solution I'm going to go for. I think it's because the PyInf, all the PyInf did was from the previous. Maybe I need to redo. Wait, hold on. But PyInf is working. Right, PyInf is working. So you know what I'm doing? I'll end this. Let me figure this out. I'll see you guys tomorrow. Adios.